All right, so keep in mind we're not doing every section of chapter 4. We're skipping the even sections. So this is 4.3, quadratic functions and their properties. And we'll see this, but before I get started, simplest way to think of quadratic functions, ax squared plus bx plus c, or in its completed square form, or what the book calls the vertex form, x minus h squared plus k. The second format, well, it shares the whatever the value of a is, but it gives us different numbers than b and c. It gives us numbers that makes graphing and answering other questions about the function much, much easier. So you definitely need to immediately think of both of those things when you see quadratic function, both forms. All right, objectives, graphing the function using transformations, or I suppose using this function. Identifying the vertex, axis of symmetry. Those, we'll see how we do that, but it's not uncommon for a website in particular to ask you questions about the graph without actually having you graph it. So it's pretty common that you have to answer a question, for example, what is the vertex? And that's just an easier question to ask and grade than to actually ask you to graph the function. Axis of symmetry is related, and we'll get to that. So the rest of this are questions that you'll see in advance, but you'll see on the homework, but I'll just go on. All right, so the book is giving you the first equation I had given you. The quadratic function is, when it's written in its polynomial form, where we write the exponents, you don't have any parentheses here, and you just write decreasing powers of x. This is your quadratic function. A, b, and c are real numbers. If a were 0, this wouldn't be a quadratic function because this term would be missing, and you would have the highest degree would be 1. So it's really important that you see that. Now, b and c could be 0, so let me just quickly write, f of x equals 3x squared is a quadratic function where a is equal to 3 and b and c are equal to 0. That's okay, it's still quadratic because, of the rules here. And we'll talk about that example again. Oh, they're talking about it right now, so okay, there it is, 3x squared. So drawing just the monomial, the single term of degree 2, looks like this. It's going to be a parabola. Depending on what you're multiplying it by, has an effect on stretching the parabola. We would usually refer to that as a stretch by putting the number there. So 3 stretches the graph. So if I were to, fit these in a box, the black one would appear stretched vertically, meaning if I kept on, working on here, the black one would be, narrower along the x-axis, but stretched along the y-axis. A minus sign, in other words, if a is less than 0, the parabola. Now this is a tricky wording, tricky thing to word. We talked about this earlier, that this parabola is increasing. Let's look at the red one here. It's increasing because we're talking about traveling from left to right. It's increasing until it levels off, and then it's decreasing. So if I have a parabola going like this, I can't say it's a decreasing parabola. And we don't use the word decreasing. We use another name for it, called concave down. And concave down means that, well, it doesn't hold water is one way to think about it, but it's pointing down this way. And this one here is concave up. It does hold water, but still that whole thing about increasing and decreasing and average rates of change would still hold that the function is increasing on part of the interval and decreasing on part of the interval. So again, it's a word we'll see, but just so you see it, a minus sign, and you know what shape it gives you. All right, so when you have a graph, yeah, they're talking about, they even put it in quotes, the graph opens up when a is greater than 0, and it opens down when a is less than 0 or negative, just what you would think. Now, it's interesting how they did talk about a vertical stretch if a is a larger number, and it's vertically compressed if it's a smaller number. Right. Pretty natural if you just see a few of these. We are going to, oh, here's that phrase, concave up. I don't want to say increasing, because that's not the way we use that word. When you have a vertex, we're going to call this point h comma k. H is the point, the x value, and k is the y value. And so the lowest y value is, in this case, is k. So I'm going to go ahead and write something here. If I were to write the range of this, the minimum value is k and the maximum value is infinity. And that is the way you might have to answer the question. If they ask you for the range, now why is the minimum value k? Well, on the y values, the lowest value is k, and it just goes up from there. So minimum comma maximum. So we need to use these letters. Now what does h answer? Well, the equation of this line through the vertex, it's a vertical line, and it goes through a point where x is equal to h, and that is actually the answer. X equals h is the formula for the axis of symmetry. So the vertex reveals information about the range and the axis of symmetry, and those are questions you may be asked to answer, even beyond graphing and even beyond what is the vertex. You might need to answer more questions than that. All right, if a is negative, the graph is pointing down, so in this case, the minimum would be negative infinity and the maximum would be k. Because again, remember, this point is the ordered pair h comma k. So k is the maximum value that this graph would ever take on. The axis of symmetry is still x equals h. And they'll ask questions about, is it pointing down or is it concave down? They will not say, is it, well, it would be a different question if they asked if where it's increasing and where it's decreasing. All right, so more of the same ideas. By the way, it's important to be able to see this. I'm not saying you have to know it without drawing the graph, but a very, what I call sloppy graph might do. So you don't need a perfect graph to answer some questions, but you want to be able to visualize what's going on with the graphs, and just a quick sketch might reveal a lot of the information that I'm saying here. All right, so we start off with this equation given to us the way you, well, some of you might expect to see an equation, y equals, or f of x equals ax squared plus bx plus c. But remember, that's worthless when it comes to graphing. That's not the format that's going to answer any questions in terms of graphing. So it looks like they went through this process in the most cumbersome of the manners we have, completing the square. Completing the square will get you there, and when I say there, I mean it will reveal the format ax minus h squared plus k, but hopefully that's not the only way you would approach something like this. So just to walk through what they're doing, they start with an equation without the parenthesis, without the perfect square. Should look here. And the only thing I know from the original problem to the transformed equation is that a is equal to 3. So a is equal to 3, and I always knew that. The other thing I knew is that there would be an x here, just from the equation. There would be a 2 there. And that's it. I don't know my h or my k. So how did they do it? Well, they completed the square. Start first by putting the 3 where we knew it had to be, factoring out the 3. By the way, this 3 was not factored out because it was the greatest common factor of 3 and 6. It was factored out because we knew we wanted x squared here. So in other words, even if this created a fraction, we would factor out a 3 just to make that 3 was there. All right. Gives us kind of something that's kind of looking like what we want. But notice there's no square, there's no exponent here because all he did was factor. The only way to get that to be a square is to complete the square. So the process, of course, is take the 2, cut it in half, and square it. So 2 divided by 2 is 1. 1 squared is 1. We just created a trinomial. Now, this is a little tricky because it's not what you expect. But what was the impact of putting that 1 here? Remember, everything inside these parentheses is multiplied by 3. So by putting that 1 here, I just added 3 to this side. I added 3. I didn't just add a 1, I added 1 times 3. All right, to make up for that, I have to subtract 3. So these placements here, this 1 placed here to complete the square, and this 3 placed here to counterbalance that, were both required at the same step. All right, it's called completing the square. Anyhow, we complete the square. This is x minus 1 squared, and then 5 minus 3 is 2. And remember how, did I give it to us? Yeah. Remember what that graph will look like. Okay, they're graphing this by transformation. I'm just going to go ahead and say it. If I match this up to this equation, we can see that h is equal to 1. And if we match this plus 2 with this equation, we'll say k is equal to 2. And so what that means is the vertex is 1, 2. Now what the author's doing, the author's going to talk about that, but prior to getting there, the author uses transformation. So this is a technique that might not be the technique that we'd all gravitate towards, but the author says, oh, this is a transformation, 1 to the right and 2 up. Just explaining the process here. So you're taking the basic equation without any numbers in it. You're saying, well, what would happen if I subtracted 1 from x? Oh yeah, it's a shift 1 to the right. What's going to happen if I multiply by 3? Oh, it's going to stretch these points up 3. And what's going to happen when I add this 2? Well, it's going to move the previous graph up 2. And it's going to move these dots up as well. So we get this graph through transformations of the original function we know and love, y equals x squared, and see the numbers. All right, so some of this was predictable. Again, 3x squared, we kind of know what that's going to look like. We know what x squared looks like. We know what multiplying by 3 will stretch it. So, but that's not enough. We also needed to know where the vertex was. Axis of symmetry is this line. If you have the picture, you're good, because you can just draw the line, and you can tell yourself the equation of the line is x equals 1. But what I'm saying is we knew the equation was going to be x equals h all along. So even without the picture, I knew that answer for the axis of symmetry. All right, so now they're introducing the format that we got by completing the square. But notice this. They're saying, you know what? You don't have to complete the square to transform this into this. Like I said, you already know what the a is going to be. You just don't know what the h and k are, but there are formulas that give you h and k. And using this formula will prevent you from having to do that whole thing about completing the square, that whole process of completing the square. It's not a long process, but this process of taking this, factoring out the 3, it can be pretty tedious if there's a fraction involved. So I can guarantee the author's not going to do this when the problems get tricky. The author's going to use a different method. The method of formulas. All right, so again, these are the same two formulas you need to know, but here's a formula that will tell you what h is, and here's a formula that will tell you what k is. Now they kind of back off on this formula right here, and I'll explain why. In other words, if I were to rate these as important, I'd give this one a 10 out of 10, and I'd probably give this one a 4 out of 10 in terms of importance, because there's a different way to get k, and that's what they're talking about here. They're saying if you call this h, there's a formula for h, and remember we saw this, if I call this k, there's a formula for k, but there's another way I can find k. I can just substitute the calculated value for h into the function. So I'll try to demonstrate that when I do a problem. All right. So this example is just worded differently. They're trying to take you down the road of not completing the square because of the way they asked. Now you could complete the square, factor out a -2 and do all that, but they're saying without graphing it, find the vertex and the axis of symmetry. All right, so this is the first time we've seen the formula in action. They take this formula and it's minus b over 2a. So b gets substituted. The minus signs here, 2. All right, well, you get 2. Now what I'm going to do is I'm going to immediately take that 2 and substitute it knowing it's going to be the vertex. And what I mean by that is, remember, h is the x value of the vertex. So if I just take that 2, put it in the table, take that 2, plug it in, I will find the vertex. Now let's see how they went about it as well. They did the same thing here, more with function notation here. But if you plug in 2, f of 2, in all of the spots, this is going to be 8, this is going to be, or -8, it's going to be 6 plus 16 minus 3, and that is going to give you 5. So what I'm saying is, I used a formula here, minus b over 2a, to find this, but notice what I didn't use. I didn't use that formula that I gave a 4 out of 5 to. I did not use this formula to find k. I found k instead by taking f of h. And not literally f of h. If f of h, if h was 2, I just found f of 2. So when you find h, you can plug it in to find k, and that's why this formula is very important, And this formula is almost optional because we have a more typical way to find it. All right, the axis of symmetry, we don't even have this thing drawn yet, but what I'm saying is you can just kind of very casually, without even an x and y axis, understand that if this is 2, 5, the axis of symmetry is this line, and that line would be x equals 2 because it's a vertical line and it has a 2. It goes through a point that has 2 for the x value. Well, actually, this would not be a good picture because the picture is, I didn't take into consideration that a was negative. It's still the correct vertex, but since a is negative, my rough sketch should have gone this way. Still, 2, 5, still the axis of symmetry is x equals 2. And I guess that actually strengthens my point. I can answer questions about the vertex, the axis of symmetry without a good graph. I mean, neither of these are good in that they are not even on an XY axis, but they are adequate for answering the two questions they ask here. What's the vertex and what's the axis of symmetry? So I'm actually a little surprised on a problem like that. Almost every book is tempted to draw the graph, and they never did because that wasn't the question. All right, x-intercepts aren't terribly important in this section. I mean, if we weren't moving forward in the book, I might have left them out, but no, they are very important in later sections. So no surprise, they're going to ask about the x-intercepts. So to find the x-intercepts, that's when this side of the equation equals 0. Now, the good news is we have a lot of experience setting ax squared plus bx plus c equal to 0. We can factor it. We can use the Pythagorean theorem. We can do quadratic formula. We can do a lot of things with it. But the author's talking about part of the quadratic formula called the discriminant. This is the part that resides under the radical sign. It's x equals minus b plus or minus the square root of the discriminant. And so this thing that resides under the radical, if it's positive, you're going to get two answers because you're taking minus b and you're adding and subtracting a number. When I say it's positive, I mean the whole discriminant's positive. If the discriminant is negative, well, then you do have a problem because you wouldn't have a real number in this calculation. And if it doesn't give you a real number, how do they say that? The discriminant is negative or less than 0, so it has no x-intercepts. So again, to find x-intercepts, you set ax squared plus bx plus c equal to 0, and however many solutions this has is the number of x-intercepts you have. And again, very popular thing to do in an algebra class. In fact, I couldn't imagine an algebra class where you didn't solve, ax squared plus bx plus c equal to 0 at least 40 times. It's just one of those things that we do when we need to do it. All right, so they gave us an example of, the vertex. Again, it's h comma k, where we have a formula for h, and we calculate k by substituting h. All right. Parabola, two points because the discriminant is positive. It just touches without crossing the x-axis when the discriminant is equal to 0. And this would be an example of no x-intercepts. By the way, this idea of no x-intercepts would come about without the analysis of the discriminant. So I just want to make sure you understand that. If I said, here's a vertex in quadrant 4, and the graph, or 2, quadrant 2, and the graph is concave up, you would instantly know there are no vertex, no x-intercepts, because they didn't cross the x-axis anywhere. But that's exactly what we want to look at when we have a problem like this. We might not need the graph, and anytime you can answer a question without needing the graph, it reinforces the graph, and it's considered a win. So graphing a quadratic equation using its vertex, axis, and intercepts. I'm going to pick up on this because this video is getting a little long on part 2 of this. So already done part 1. I mean, this is part 1, and we'll pick up with part 2.